Okay, imagine there's a huge hot ball hidden inside the Earth. It's floating in an ocean of molten metal. This ball also spins on its axis, but it moves faster than the rest of our planet. This is what the Earth's core looks like. The solid metal ball is the inner core, and it's 750 miles thick. That's roughly the distance between New York and Chicago, and the whole thing is made up of hot iron and nickel. The outer core is the molten ocean. To reach the edge of it, you'd need to dig a tunnel into the Earth that was about 3,700 miles long. But you would hardly want to go there because it's the hottest point on the planet. The core temperature is 11,000 degrees Fahrenheit. That's greater than the surface temperature of the Sun. Another incredible thing about this place, the gravity at the outer core is 3 times stronger than that at the Earth's surface. This means that if we could somehow find a way to live near the core and you threw a stone there, it would fall 3 times faster than normal. It would become 3 times heavier. You would also become 3 times heavier. Now that doesn't bother you so much because things far worse will soon happen. Living conditions in the core would be the exact opposite of life on the International Space Station, and it'd be a lot harder than living on the surface. It would be difficult for you to even hold a fork in your hand because of just how heavy it would feel. Eating lunch would become a serious challenge. You'd break into a sweat just from writing with a pen on paper or typing on a computer. But if people could ever get used to these conditions, they'd become a lot stronger. Humans have learned to use the heat coming from inside the Earth as a source of energy. Some companies use this energy to heat water, which creates steam. This steam is used to power turbines that produce electricity. If the core ever cooled down and that heat disappeared, this kind of electricity might become very expensive. Some parts of Earth might become very dark, as people went back to using candles and fires to light things up at night. And you could forget about using your electric car as well, because charging it up would be just too much money. Phones, computers, the internet, all these things would cost a lot more. But this would actually be the least of our worries. Oh, just wait for it. The hot core's rotation creates the Earth's magnetic field. This field is like a shield that protects us from the sun and outer space. If the shield disappears, solar and cosmic radiation would pass through the atmosphere. The electricity supply would become seriously unstable. Microwaves, televisions, kettles, traffic lights, and computers could all be damaged. The screen of your laptop or phone would turn on and off randomly. Videos could freeze, and the batteries could run out in a second. Satellites would stop working, which means there wouldn't be any GPS system to rely on anymore. Say goodbye to navigating with your phone's map. Radio equipment would also stop working, so you wouldn't be able to make calls or send messages. Even now, when our magnetic field is working normally, solar flares can still create magnetic storms that disrupt electronics and affect people's health. Some people are sensitive to these storms and can get really bad headaches. If the magnetic field disappeared completely, every person on the planet, along with plenty of animals, would get seriously painful migraines. Scientists would have to invent special helmets that protect people from exposure to the magnetic storms. If the core cooled down and you became lost in a forest, it would be really difficult for you to find your way home even with simple equipment. Without the magnetic field created by the active core, your compass needle would no longer show where north, south, east, and west were. You would see the birds in the sky going crazy. They wouldn't know what direction to fly in for the winter, because south would no longer exist. In fact, no animal would be able to migrate anymore. In the sky, the location devices on planes would stop working. That means no more air travel until people find a new way to navigate. But hey, let's look on the bright side, because that's what we do here. You wouldn't have to go to the North Pole to see the northern lights anymore. Auroras would appear in the night sky everywhere. These occur because charged solar particles run into the magnetic lines stretching from north to south. But these lines will disappear if the Earth's core cools down, and the particles will light up the sky all over the world. A frozen core also means the tectonic plates will stop moving. There will be no more earthquakes anywhere in the world. But that's not as good as it sounds. The movement of these plates creates faults on the Earth's surface. They give us access to important minerals. With no more movement, producing fuel could become a lot harder. The price of gas might go up. Most people would have to stop driving their cars. There would be a lot more bikes and horses on the road, maybe some llamas. Volcanoes would also stop erupting. If the core cools, the magma cools. People who live near large active volcanoes would no longer need to worry so much. But there would be a downside to this. Volcanoes contain a huge amount of useful substances and minerals. The soil around volcanoes is very fertile, which is really good for agriculture. So more people would now have to eat artificially created food. There would be big problems with the supply of natural food products. Only rich people might be able to afford that classic tomato and cucumber sandwich. But the worst thing would be the long-term exposure to radiation, which is seriously bad for our health. More radiation means that the risk of getting diseases would be much higher. People would have to build special shielding to protect themselves from solar radiation. It would be way too expensive to cover the whole planet with this technology, so we just create separate shields for each city. Just imagine the side of every city covered by a huge protective dome. In this radioactive world, movement between cities would only be possible in special closed transport. People would need to wear protective suits. You wouldn't be able to go to the countryside anymore. Anyone still living in a village or small town without much funding would be forced to live underground to protect themselves. Plants and animals would also have problems. Herbs, flowers, and trees would receive huge doses of radiation and wouldn't be able to bloom. Livestock wouldn't be able to eat grass and hay. Milk, cheese, and yogurt would be in real short supply. Plants would have trouble producing oxygen. The magnetic field not only protects us, it protects our atmosphere. A frozen core and no magnetic shield means that the solar wind would destroy the atmosphere in a few hundred years. The conditions on Earth would be changed completely. Humanity would no longer venture outside its protective domes with their artificial atmosphere. Instead, we'd have not only our cities, but also the last surviving pieces of nature, our trees, lakes, grass, meadows, and flowers. Everything left outside the domes would turn into a scorched desert. This is what happened to Mars. The red planet has no seas, oceans, and lakes. Some scientists believe it's completely dry because its magnetic field disappeared. With no protection, Mars lost most of its atmosphere, and the sun's wind swept away all the surface water. But of course, this is just one of many theories. This took place billions of years ago, and no one can say exactly what happened. But don't worry, our planet won't turn into Mars anytime soon. The Earth's core is cooling very slowly. It will take another 2 billion years or so before it cools down completely. What's weird though is that our magnetic field can be unstable even today. In the southern hemisphere, there's a spot where the magnetic field is weak. This place is called the South Atlantic Anomaly. Charged solar particles flow through this spot, which can cause problems for orbiting satellites as they pass through. There are some other places like this around the world, but fortunately, they don't cause us any really big problems. Good thing.
The Earth has 3 main layers. 2 parts of the core, the dense, hot inner core, and the molten outer core. Then comes the mantle. And then follows the thin crust, the surface that supports life as we know it. At least, that's what we thought, because now scientists found a new mysterious layer located deep within the solid inner core. Earth's inner core is approximately 2/3 the size of the Moon. And made of nickel and solid iron, it's burning hot. The temperature at the center of our planet is the same as at the surface of the Sun. The outer core can reach almost 10,000 degrees Fahrenheit. It's difficult to explore it because we can't go there, and it's like looking through a really dirty window of 3,200 miles of molten metal and rocks. But we can rely on laboratory experiments on heated pressurized rocks, signals from seismic waves, and computer models. When an earthquake hits, it sends out seismic shock waves. Those waves travel through layers at a different speed, depending on the direction they go and the material they move through. In the new study, a team of scientists set a data set of 100,000 deep earthquakes. Some of them went over 60 miles below the surface. When an earthquake happens on one side of our planet, scientists track its waves all along to the other side. Waves change when they come to the other side, so scientists try to understand the materials these waves have passed through. They found a new layer in the core of our planet thanks to earthquakes. Normally, shock waves travel along the equator, but down below, they digress and go into different directions, about 60 degrees to the side. When waves pass through the inner core going from north to south, they will travel more quickly than waves going through the core parallel to the equator. It's important to understand the core because it creates our magnetic field, which in turn protects the planet from things like solar winds that are charged particles coming from the sun. In the 1960s, we discovered the Earth pulsates every 26 seconds. It's like clockwork, a giant heartbeat. The ground is slightly shaking, but we mostly don't feel it. Researchers can still track it. Some of them think the continental shelf comes as a huge wave break under the oceans. For example, the highest part of the North American continent falls off into a deep abyssal plain. One theory says waves hit this spot, producing regular pulses. It's like having all kinds of drums. You hit them with your hands and accidentally slam that one spot that produces the right harmonic bang to rattle our entire planet. If this theory is true, we're lucky there are no more spots like this that can shake the Earth. Other scientists believe the pulsation happens because there's a volcano near the critical spot, the island of Sao Tome in the Bight of Boni. You're walking, running, and jumping, but when you stop, it always feels like you're standing still. In reality, you're moving even when you're perfectly still because our planet is always on the move. Depending on where you're at, you could be spinning through the universe at more than 1,000 miles per hour. If you're on the equator, you'll move the fastest. Let's say you have a basketball spinning on your finger. Check the ball's equator. A random point on it has farther to go in just one spin than any point near your finger. That means the point on the equator is moving more quickly. The Earth is a planet that recycles all the time. The ground we're walking on is recycled. Our planet's rock cycle turns rocks of one type into another. That's a cycle that goes on and on. The depths of our planet are filled with magma. As magma is going out onto the surface, it hardens into rock. Tectonic processes like volcanic activity, earthquakes, mountain building, and all of the other processes that shape the surface of our planet bring that rock to the Earth's surface. When the rock is on the surface, erosion shapes it and shaves its bits off. Those small particles then get deposited. All the pressure coming from above compacts the particles into sedimentary rocks, like, for example, sandstone. Sedimentary rocks can also end up deeper and deeper under the Earth's surface. Since there's a lot of heat and pressure, they get cooked into metamorphic rocks. They can go back to the surface once again, or even end up being re-eroded. Sometimes the crust plates are pushing one under another, and this way, rocks can transform into magma once again. We've explored only 5% of the ocean so far. The ocean itself, as well as life below the seafloor, is still a mystery. The sediments that are underlying our oceans are home to different microorganisms that exist even at depths of 1.5 miles beneath the seafloor. There are microbes hidden deep inside volcanic rocks below the seafloor off of the parts of the Pacific, hidden under 870 feet of sediment. The biosphere under the seafloor is growing extremely slowly compared to life on the surface. Cell division happens every 10 to 1,000 years. Something's different about the Earth's axis. Climate changes and melting glaciers, mostly in the regions like the Himalayas and Alaska, made the axis shift. Our planet has two kinds of poles. Are the south and north magnetic poles. They affect things such as drift and navigation. The axis that the Earth is spinning around is another kind of pole. It shifted a little bit over time, but we don't know exactly why. Researchers realize there are moving masses of water pushing the Earth's axis eastward. Take a basin of water as an example. If you're moving it back and forth, sloshing makes the water move its weight all around. A similar thing is happening on a planetary level. No matter how large an earthquake is, no human could ever feel an earthquake on the opposite side of the Earth, although some people claim they did. In 2013, there was one near the Kuril Islands with a magnitude of 8.5. It went around 400 miles deep. It was so strong, people in Australia reported they could feel the ground shaking. The strongest earthquake happened in Chile in 1960 with a magnitude of 9.5. The rupture zone stretched from 311 miles to almost 620 miles along the country's coast. Earthquakes with a magnitude of 10 or higher can't happen. The magnitude depends on the length of the fault where it occurs. The longer the fault, the bigger the earthquake. A fault is a break in a part of the planet's crust. It has rocks on both sides, and they move past each other. We haven't found a fault long enough to generate earthquakes with a magnitude of 10 or more. If it happened, it would extend around most of our planet. An earthquake with a magnitude of 12 would require a fault larger than our planet. One side of our planet is getting colder than the other. The Earth has a system that keeps it warm from the inside, a red-hot liquid interior deep below the surface. It spins and, at the same time, generates a magnetic field and gravity. That way, the Earth's core holds the atmosphere closer to the planet's surface. The Earth also absorbs heat from the sun, mostly on the surface. The heat doesn't spread equally on all parts of the Earth. One side of the planet, the Pacific Hemisphere, is losing heat more quickly than another, the African Hemisphere. This happens because land traps more heat than the surface under the ocean. The seafloor is way thinner than the landmass. Also, the temperature caused by the heat coming from inside the Earth is getting lower because of huge amounts of cold water above it. Clouds are not just like some fluffy distant pieces of cotton. They weigh more than 1 million pounds and help regulate our planet's temperature. If you take all the water droplets in clouds and bring them to the surface, you could cover the planet with a liquid layer as thin as a human hair. It doesn't seem like a lot, but this water is crucially important for climate. We'd have warmer temperatures if it weren't for the clouds.
Today, we're going to work our core, so get ready to sweat. Oops, sorry, wrong core. Hey, we've traveled far and wide, down to the Earth's inner core and up into outer space. But what if we could combine these adventures and find out what hides in the innards of other planets and moons in the solar system? With the help of this interstellar hyper drill, we can achieve that, at least in part. Coordinates are in, all systems ready, and our first destination is the Moon. Our moon, in fact. We land on its gray and desolate surface under the black sky. No blue here because there's very little atmosphere to disperse the light. The drill starts working, and we first go through the outer layer of the moon, the crust, just like on Earth. We're on the sunny side, so the thickness of this layer is only 43 miles. But were we to land on the dark side, it would be more than twice as thick. The moon is a rocky body, so its crust is largely made of silicon, iron, aluminum, calcium, oxygen, and magnesium, with much smaller amounts of other elements. Further down, we find the mantle, and it's a long and tedious journey through. This layer is about 850 miles thick. It gets hotter as we go deeper, finding composite minerals, pyroxene and olivine. They're made of iron, silicon, oxygen, and magnesium in different proportions. Finally, we break through the hard layers and into the semi-molten outer core. Another journey of about 93 miles ahead through this scalding swamp. And we dive into the iron ocean of the liquid core shell. It's nearly 60 miles thick, and the molten metal threatens to evaporate us. But this drill was made to sustain an extremely heavy onslaught. And that's how we finally come to a sudden halt. In the deepest reaches of the moon, there's a solid iron core, which is 150 miles thick. We could drill through it, but it would be unnecessary. So we just set the flag here and skip to the next planet on our drilling list. And it's Mercury. It was hot deep inside the moon, but on the surface of the smallest planet in the system, it's even hotter. That's because it's so close to the sun, of course. Alright, let's drill. Mercury has a pretty thick outer shell, which is both crust and mantle, going about 250 miles deep. Not the most fascinating journey, it's not unlike the Earth in many respects. But then, the drill stops, ramming into a solid metal wall. It's Mercury's core, which has a diameter of over 2,500 miles. It takes up to 85% of the planet's overall diameter. No use trying to drill through this one. It's fully metal and extremely dense. Skipping to the next planet, and we're on Mars now. Oh look, it's sunset here, and the sun is making the sky hazy blue. But you know the drill. I mean, we're here to drill. So that's what we do. Mars's crust is quite thin compared to Earth's, just 6 to 30 miles deep. Its composition is much the same though: iron, aluminum, calcium, potassium, and magnesium. That's one of the reasons why humans are looking to colonize the red planet one day. It's very similar to our own. We're very quick to drill through the first layer, and the second one, the mantle, is now upon us. It's a hard and rocky layer about 1,100 miles thick. Thanks to its size, Mars isn't seismically active any longer. There's simply no magma boiling close underneath the surface of the planet, making it silent and docile. It's a long dig, but we finally come to a screeching halt, bumping into the core. A ball of iron, nickel, and sulfur with a diameter of 2,000 to 2,600 miles. This core is bigger than that of Mercury, but the planet itself is larger too, so it figures. Okay then, our next stop is even more interesting, because it's Jupiter. This gas giant has a mass twice that of all the other planets in the solar system combined. And we landed right in the middle of an ocean. The ocean, I dare say, it's the largest one in the whole system, and it's made of liquid hydrogen. The drill goes smoothly through the surface of the planet because there's no rock or hard metal here, only gas and liquid. But the shaking, yikes! The pressure on this planet is more than just huge, it's unimaginable. The drill is barely able to withstand it, and as it's going deeper, the pressure's becoming higher too. We've reached Jupiter's core, and it's nearly too much to bear. The temperature here is about 90,000 degrees Fahrenheit, and the core itself is not solid but liquid as well, kept together by the immense pressure from all sides. The drill starts to rattle. Bad sign. Let's get out of here before it breaks. Whew! No winds, no pressure, no heat. All around us is a vast icy wasteland, crisscrossed by ridges and reddish bands. It's Europa, one of Jupiter's most promising moons. As we drill through the ice, let me explain. Europa is one of the candidates to have extraterrestrial life in the solar system, and it can be found right beneath the icy shell through which we're now digging. It's only 10 to 15 miles thick, while down below is an enormous saltwater ocean, twice bigger than all of Earth's oceans combined. The deepest point on Earth is Challenger Deep, and it's a bit over 6 miles down. The ocean on Europa, on the other hand, can be up to 100 miles deep. Who knows what can be lurking in that deep, dark sea? Anyway, we travel fast through the water and finally reach the bottom of the ocean. The mantle starts here, and it's made of rock, just like on Earth. And not much deeper in, we find the metal core of the moon. Europa is a little smaller than Earth's moon, so it's no surprise we reach its center pretty fast. Okay, skip drive on. Let's go further. Oh, I'd rather we drill in as fast as we can. Just look around, it's blazing here. We're definitely on Io, another moon of Jupiter, and the most volcanically active world in the solar system. Look, that volcano is twice the size of Everest, and it's erupting right now. Thankfully, we're under Io's surface already, but that's not to say we're safe. It's all molten down here too, mostly yellow and brownish hue, due to the huge amounts of sulfur. The stench must be horrible. Anyway, the most peculiar feature is that both inside and outside, everything's always on the move on Io. Jupiter and its other moons create tremendous tidal forces, making the surface of Io swell over 300 feet up and down. Like the largest tsunamis on Earth, only here it's not water but rock. The deeper we go, the calmer it gets though, until we're finally at the iron core. It's still hot here, but at least there's no shaking and swelling like above. Let's put up another flag and go to the next point. And that would be Saturn, the second largest planet of the solar system and the one best known for its spectacular rings. Not the only one to have them at all, mind you, but we'll get to it. Now, as you've surely noticed, Our drill is simply falling down through the gaseous hydrogen and helium, making up most of the planet's surface and atmosphere. No need to work here, just wait and hope the immense pressure won't crush our drill to a hunk of junk. At last, the pressures become so enormous that we find ourselves in the liquid hydrogen, and here we start diving. Soon we'll reach the solid core of Saturn. Here we are. It's made of iron and nickel and is actually quite small compared to the rest of the planet. Well, the last destination awaits, so come on. And here we come, Neptune. The drill immediately deploys anchors because the winds here are extremely powerful. They reach speeds 5 times greater than the most devastating hurricanes on Earth. Neptune is covered in a pretty thin layer of hydrogen and helium, just like Saturn or Jupiter. But underneath, there's much more than that. It's hot, windy, and lonely here on the outskirts of the solar system. So let's dig already. Beneath the gases, there's suddenly a bubbling hot mass of water, methane, and ammonia. Phew! These substances are hot, despite Neptune being called an ice giant. The name comes from its core. Deep inside, where we're quickly headed right now, a small ball of rock and ice sits all alone. And despite the boiling temperatures above, the ice beneath is ever cold.